So this one simulation that tries to build something like our Milky Way galaxy. But in the beginning, it's small, but over time, gas keeps falling in, and it's growing the galaxy. The galaxy grows over time. So our galaxy is like a cannibal. Because sometimes there's a small galaxy and it gets eaten up by the big galaxy. And it's doing this even as we speak right now. There are galaxies that are joining our Milky Way. And so now, after 10 billion years of growing, we now have a galaxy that resembles the Milky Way. And now it's more slowly accreting or getting smaller galaxies. And this just shows that sort of looks like the galaxy, and it's going around. And it is sort of the right size. So it takes 100,000 years for light to cross our galaxy. So what I have to say though, for these computer simulations, they're still very rough. Meaning, we don't really understand yet how, for example, stars are formed. So we have our guesses, and that's what these codes do. And in fact, we can also resolve or compute down to the smallest scales because it takes too long. So this particular simulation took 8 months to do in a supercomputer in Zurich, because they have to calculate each time step and all these dots. And if you do it in your regular computer, it will take 170 years. So these are really the big computers, and it takes 8 months to do one galaxy. And it's not even the right, I mean, this is okay, but it doesn't get all the right properties. So the challenge is how to do this for millions of galaxies. And in this sense, in this field, observations are ahead of theory. Meaning we have the observations, we see all these galaxies. The question is, how can our models reproduce those observations? And there are ways, of course, but that's work in progress. And this is state of the art, that we can do something like this. So that gives you a flavor of where we are in understanding how galaxies form. And now, just to give you a sense of where we are going, where is the Milky Way going? So I'm showing this picture of our neighboring galaxy, which is called the Andromeda Galaxy. It's also a big, beautiful spiral. And when we measure where it's going, we see that it's going towards us. And in fact, we are moving, the Milky Way and the Andromeda are moving towards one another. So you can imagine what will happen in the future. And we see this. These are two other spiral galaxies that are merging. And so we are scientists, so we try to model this. And what I'm going to show you is a video of the future of the Milky Way and Andromeda. So in this video, we have the Milky Way and Andromeda, two of these galaxies, and we play time. Okay, we can fast forward time to see what happens. So gravity, again, it's gravity that's attracting the two towards one another, and in 3 billion years, so they sort of do this dance, and you get these tails, tidal tails, that get wrap around. and over time, they will merge and form a new galaxy. We can call it the Andromeda. That is bigger, of course, because it combined the two stars, and also it will become a red elliptical galaxy. The spiral structure will be gone, so we'll get something like this. So you might be asking, what happens to the Earth? What happens to the solar system? The first thing to know is that we won't collide with any other star because the stars are too far apart. So this happens, the stars don't collide. Okay, the galaxy collides, but the stars don't. Because there's a lot of space between stars. So we'll probably survive that collision. And then the next question is, where do we end up? So we could end up, the danger is we end up near the center. There's also a big black hole there. And also lots of energetic, high energy rays. So that could be bad for life. The other hand, we could end up right here. So then it will be lonely. No more stars, but you will see like this blob in the sky. Oh, that's our galaxy. And then there's very little chance that you get flung out of the galaxy altogether because of these interactions, and then you'll just be floating like a rogue planet. But they've made the calculation, the most recent estimates say that we'll probably be in an orbit that's not too near. So we'll continue to move around the center of the galaxy and just watch the things happening there. So we'll probably be okay. Until 2 billion years or so after, you may know, the sun will blow up. That's around 5 billion years. So this will happen around the same time. But it's a long way. So it's not 2012. This is billions of years ahead. But again, with our computers, we can do this. We can see what will happen a long, long time from now. And in fact, we see this happening all the time. Galaxies merging in this project called Galaxy Zoo. If you go here, you can see these images. And you can actually help science. You can become a citizen scientist, they call. Because what happens is there's so much data, there's not enough scientists' eyes to look at them. So they put it on the website, it's called Galaxy Zoo, and then you can identify these things. These are things that were identified by computer users and said, oh, this is interesting, this is interesting. And so they were able to compile these merging galaxies. So that's it. That's our journey today. We talked about where we are in the universe, where galaxies come from, and where the galaxy is going in the 5 billion years. Thank you. Just a bit of a plug to end. Where we are going in human years in the next 2 years or 4 years is I'm part of this survey, a collaboration, a project of scientists that just started. It's called the Dark Energy Survey. We have a telescope in Chile. And we put a new camera on this telescope. It's the biggest camera in the world. It's, I don't know, about I think 700 megapixels. If you convert it to camera, right? But we will use this to image the sky. Right, it's this big. This big. And we turned it on. We call it first light, and this is one of the images that it saw. And so we're very excited to get data, and this will be used to understand, again, because it's bigger, we see more, we see deeper, we see farther. And so we get to trace how galaxies form. And also, we want to use this data, we're going to use this data to try to learn more, understand the nature of dark energy, this mysterious thing that's making the universe accelerate. So tune in for science from that. And that's it. Thank you very much for. And I'm happy to take questions. Take questions from the audience. Good. Just start. Yeah, please. You can shout, or there's some mic that maybe. This one is not. Hello. I'm here.
Okay. My question is, you explained the birth of that universe using the Big Bang Theory, and you also explained that science had to assume the existence of 73% of dark energy. I'm wondering, are there other theories that can explain the universe as it is, also to a certain degree, other than the Big Bang Theory?
Right. So, the Big Bang Theory is very established. I mean, it's the picture we have, and it explains everything we see. Again, with this dark energy, as you said. But as actually I mentioned earlier, there's an alternative theory where you don't have dark energy, and that is you change the laws of gravity. Okay, because the thing is, when you use the laws of gravity we have now, which is Einstein's general theory of relativity, you get expansion, but the expansion slows down. It doesn't accelerate, doesn't become stronger because of gravity. Gravity actually pulls things together, so it becomes slower and slower. If there's more matter, it will actually eventually contract again, and we have what we call the big crunch. Right? But from our observations, we think there's not enough matter to do that. So what will happen, it will just slow down and just become flat, meaning slower and slower and slower and slower. All right? But in 1997, when they observed these supernovae, bright exploding stars, very well, and they know then the distances, they found that the expansion is speeding up, it's actually accelerating. So it was a surprise. So people scratch their heads, what's happening? And the simplest explanation is you add constant, this cosmological constant, in Einstein's equations. So you just put a constant, they call it lambda, okay? A Greek letter, because they do that all the time. And then it works beautifully. And this is what we call now dark energy, make it more sophisticated name. But the idea is, dark energy can be not just a constant, it could be a field that changes. But a constant works. And then last year, these people won a Nobel Prize for discovering the accelerated expansion of the universe. It's one of the biggest discoveries in the decade in our time. So the alternative theory is, if you change general relativity, if you change the theory, and in this new theory, the expansion accelerates, right? Then you don't need the dark energy. This is what we've been exploring. More theorists are exploring these so-called modified theories of gravity. And the simplest ones are, they just change the equation of Einstein, because Einstein did this equation, and then you add another term. These are called f of r theories, and then you can get acceleration. But again, it's hard because the problem is general relativity works so well in the solar system. It's the most tested, most accurate theory we know. It just works. So you cannot change it, because if you change it, then you will fail the tests here. So now they're coming up with theories with a model that would change it in the big cosmic scales, but will not change it in the solar system scales. But again, this is becoming hard. But This is already there. And this is the paper we did. The project we did is to test general theory of relativity on the large scale, so these galaxies I showed. And we showed that it's consistent with general relativity. So again, it's hard, but the error bars are big now, and you can improve these measurements. But we can even start to test these theories. So yes, it's still now up in the air. And this is the situation now. We have a picture that works, but we are slightly uncomfortable because we don't know what the dark energy is. So we are exploring alternative theories, and also, like for example, this survey, the idea is to measure the expansion better to pin down the properties of this dark energy. And that would tell us if it's slightly different from the simplest dark energy. If it's not constant, for example, if it's not constant, then they win the Nobel Prize. Because again, it will be a sign that something of a new theory of cosmology and of gravity. So this is meaning cutting edge work in the next 5 to 10 years. It's a long answer. It's interesting, yeah. More questions?
Do they know the time frame of this acceleration? I'm thinking in terms of the inflationary theory at the beginning, right, of the universe. So has it been expanding? Has the expansion been accelerating all this time, or was there another point back in the universe when it also started to accelerate?
Yes, good question. So we know this very, very well. That's the amazing thing. We know this very well from those observations. And you're right. So I go back to the slide. So in the beginning, you have the inflation, right? And there was also an acceleration here. But for some, there's an explanation. It stopped. And then, so here you have just expansion. But then, just around now, around the present, you have this accelerated expansion. So one of the puzzles is why now? And this is going to the deepest puzzle, and also why we are uncomfortable with this theory is because why they call it the cosmological coincidence, or actually the cosmological constant problem. The problem is the fact that it's only happening now translates to a value of the cosmological constant, right? This constant that we have to add in, and this value is very, very small, and it's very, very small compared to what you expect. And so that's a problem. But it's observed. We know that it has to be this small to explain this. We can actually trace this expansion like there's a plot. And that's part of the problem. And you want, ideally you want a theory that also explains why it's that small. And so scientists are in this desperate situation that they are trying, some are invoking the so-called anthropic principle, rather than also talks about. The anthropic principle says, it's more philosophical, but the idea is, the reason that the cosmological constant is so small is that if it's not small, it's too big, there would be no observers in that universe to measure it. So actually it makes sense in a broad sense. For example, if the cosmological constant is so big, what will happen is that the universe will just expand so fast, there will be no time for stars and galaxies to form. And so the thinking is no stars, no galaxies, no planets, no observers or people like us, or not necessarily people but observers, life, intelligent life that does go, I don't know. But that's the idea. The problem is that can only give you so much. So it says the cosmological constant cannot be bigger than this, but it's still this small. So why not here, 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 and here? See? So then we start to think about this. Again, you have this context of the picture of multiverse. So there are now not just one universe, but multiple universes. Could be infinite number of universes, and each universe has a different cosmological constant. And then we just happen to live in one with this small value. But then the question is why? Again, why do we live in this small value? So yeah, it's a puzzle. It's still a puzzle. But yes, we are talking about speculative theories. Yes.
So I imagine that if we're talking about the redshift, if the universe is standing at a certain constant rate, we expect the redshift to be larger at certain levels, and when we observe Andromeda, it will be the redshift. So there's also this thing in Dalton's general or special theory, which says that there's an upper limit on the speed, which is the speed of light. So how close are we to the portion in terms of the expansion of the universe? Because it's beyond the speed of light, then there's no way we can observe it, right?
Yes. So okay. It's a question of the expansion and the speed of expansion, the speed of light. Right. So the first thing is there's no limit to the speed of expansion. It can exceed the speed of light. And in fact, we do see galaxies receding faster than the speed of light. Well, actually, we do. We're close to the speed of light. Why? Well, actually, we do. Sorry. Okay, we do. The difference is the speed of light is a limit for the transmission of signal. But this is just the expansion of space. But when we measure the redshift, it can be shifting more. But you're right. Actually, I think we're not at that point. So at some point, because the expansion is accelerating, speeding up, at some point to reach the speed of light. Okay. What will happen is we won't be able to see the other galaxies, right? So yeah, I have to qualify that. But you're right. We haven't reached that point. There's a certain number of billions of years. I think it's far out. But if you extrapolate the current expansion, the acceleration of the expansion, you hit the speed of light, and then there won't be time for the galaxy's light to reach us. That's right. But actually, they will be too redshifted, meaning the light, the frequency of the light will be too small. So there will be no more extragalactic astronomy. What we will, no more jobs for. But we will have this galaxy that we have, the Milky Way and Andromeda, the new galaxy, and then some other galaxies that are part of our local group. Because we're bound together by gravity. So here's another thing. You have to think about the expansion. It's not that we are expanding, getting fatter, or the Earth is getting bigger. We're held together by gravity, so we are not following the expansion of the universe. But because these galaxies are far away, the effect of gravity is too weak, and they are carried away by the expansion of essentially of space. I also get confused sometimes.
follow-up question.
Okay.
Can we then observe, is it possible then to observe the creation of new matter? Say, if it's expanding, just this part is expanding from a beginning, right? So it can be, if it's expanding from a beginning, is it possible to posit that there's something still being created at the, as it were, the core where it started? Or was it something which was bunched initially and then?
Right, so the current, in this picture, there's no creation of matter. So was all there in the beginning, and it's just getting more and more spread out. And in fact, it's also hard to think of it as there's no center. But it's hard to think of it. But every part is expanding the same way. So the analogy is you blow a balloon, and in the balloon you have coins, and the coins are galaxies. When you blow the balloon, each coin, if you sit on a coin, you see all the other coins moving away from you. So there's no center, because here we're only talking about the balloon surface. So all the coins think it's in the center, but in fact, because there's no center. The thing is, the center is in the center of the balloon, right? Because we are in 3D, and this is two-dimensional. It's in the third dimension, so it's in a higher dimension. So, but you don't need a higher dimension. You can live in a 2D universe. In our case, we live in a 3D universe, 3 dimensions of space, right? We have north, south, left, right, and then up and down. Right, X, Y, Z. So the center would be in you can imagine it's in a 4th dimension, but there's no 4th dimension. And we cannot also imagine it because our brains are in three dimensions. But in mathematics, you can easily go to higher dimensions. And also even the string theories, they add more dimensions. They have 10 dimensions of space and 1 dimension of time. But all the other dimensions are so small, they're compactified. So you can play with these theories. But in the universe, you observe 3 dimensions of space. And there's no center. So everywhere you are, you see all the other galaxies moving away from you. That's the picture of the expansion. From the students? At the back? Nothing burning? Here's your chance. Oh, we are almost. Don't be shy. Bye. In the back. Okay.
Has the Higgs boson affected any of your theories?
My theories?
It's
To be frank, yeah, no. But we're happy it was found. So the question about the Higgs boson was recently discovered in the accelerators. And it was, in the theories, it should be there. And they found it. So it's a good confirmation of the theory. So we're happy. Another thing that would make us happy, and might change a bit the cosmology, but probably not, is if we discover the dark matter particle. So this dark matter talked about that makes up, 5 times more than atoms. We know it's there because of its gravity. So we see, for example, the velocities of stars in the galaxy are faster than you would think. And the dark matter explains why they're faster. So it's the gravity that we detect them.